So welcome everybody. While we're waiting for more participants to log on and join us, I'd like to introduce our panelists for today. Both Lisa Blecker and Sam Sandoval are going to be presenting on the webinar this afternoon on best practices and keeping pesticides out of water. Then on the pictures as shown is yours truly, Maria. I will be just presenting them and then some technical support. And to support us all is also Sarah Hernig. Okay, so we have a Q&A question. Hi, James, I was looking for you. Have we tested whether or not the polling works for those using Zoom app on iPhones? You're just on time because we have our first poll, which is up right now. And the poll question is, how are you? So go ahead and take the poll. Okay, so then we'll remove the poll question. It looks like 60% of you are doing really well. That's awesome. Okay, so welcome everybody. We've got a full plate of information for you. And in case you're wondering, I have a feeling you all know you're in the right spot. We're going to be talking about the best practices to keep pesticides out of water today. And Lisa Blecker, who is the Pesticide Safety Education Program Coordinator, and I work with her for numerous years now, she's going to be presenting, and alongside her is Dr. Sam Sandoval from UC Davis, and he is our water specialist. And I'm sure they have more merits and credits to their name, but I will let them do that and continue with the presentation. That's all yours.
Here we are. Hi, my name is Sam Sandoval. I'm a faculty. I'm also an extension specialist. Today we're going to be talking about this. So the outline of the entire presentation is what you're seeing here. California Climate and Physiography and Hydrology 101. I will be covering those topics. Then how pesticides get into water and pesticides characteristics. That will be between Lisa and I. Applicator practices to prevent water contamination. That will be also between the two of us. Please do send some of your comments, some of your questions on the chat. So let me just go right into the content. Yes, here we are in California. Basically, we have in California Mediterranean climate. What does that mean? That it rains during winter, and we will have rains pretty much one before Thanksgiving, then just a few in December, and then most of the rainfall will come January, February, March. And then we're gonna have dry summers, 6 months with the dry, clear blue sky of California. Something that it is important, and what you're seeing in this figure, is that those warm colors, they are related to moisture in the air. This moisture in the air is how we have our water. You're seeing here a moisture in the air that is coming and is hitting California. This is called an atmospheric rivers. And basically what it does is a river of moisture in the air that it is hitting California. As it hits California, in the first part, which is we are gonna be in the coastal range, the clouds will go up, and as they are going up, they are cooling down, so that's why we're going to have precipitation. Then they get into the Central Valley, and that will get, when they go down in the elevation, they will get warm. Again, they are going to hit another physical barrier, which that will be the Sierra Nevada, and then it will go up. As they are going up, it will start again cooling. It will deposit precipitation and snow. So basically that's atmospheric rivers. And you're gonna see why this is really important to understand this, because depending if we're hitting an atmospheric or river or not, you will need to adjust for the application of pesticides. This is some of the science behind atmospheric rivers. They can be 200 to 375 miles width. They usually last 2 to 3 days. And they provide between 30 to 50% of the annual precipitation that we have in California. And if we have 3 events, 3 atmospheric rivers, we're gonna be in a drought. If we have 6 or 7, we will be on a flood on a very wet year. So we are at the odds of these events. This in a different context will be the hurricanes that we have here on the West Coast. Now, a lot of this, so let me actually show you how one looks like. So what you're seeing here is moisture in the air. And this is all the moisture that is passing through. And as it is here in California, all the orography is depositing rain. These atmospheric rivers, they are also called Pineapple Express because they pass through Hawaii. So that will be another way of talking to them. These are 2 or 3 day events, and this is how we receive most of the precipitation in California. This is super important. What you're seeing here on the x-axis is the date. Specifically, we start our water year in October through September of the following year. Why is that? Because we start accounting when it starts rain until it doesn't rain, and it will start raining again. So that's why we call a water year. It starts in October, and those will be, so these steps that you're seeing here, look. So this on the x-axis is time, and on the y-axis is cumulative precipitation. So basically we are accumulating all the precipitations that happen in a water year. So if it rains 2 inches in a given month and then another 2 inches, so we're just stacking the precipitation, adding the precipitation throughout the year. As you can see, these graphs, they look like stairs. This very steep portion of it, it's because you have an atmospheric river. An atmospheric river happened, it precipitated a lot of water in less than 2-3 days, and then it doesn't rain. And as you can see here, we have in these 2 or 3 atmospheric rivers. This will be, here we go. So that will be a normal, and we don't have any normal in California. This will be the average of all the years that we have. This will be the driest years. This is 2011, 2012. It was the first year of the drought, the second year of the drought, the third year of the drought, the fourth year of the drought, the fifth year of the drought. So you can see that was the 5 years of the drought. And then after that, we had the wettest year on record. And then we have another below normal, which it was this guy here. And then another above normal. And this is where we are right now. As of today, we are below normal, 60% of the precipitation that happened in these stations compared to. Now, so the snowpack is super important in California because that's where we store a lot of water, and it gets stored in terms of snow. This will be April 11th. This will be the first, let me see, I'm just seeing here some. So basically what we have here is 2011, again, it was a wet year. And this will be the first year of the drought. These figures are taken, this is satellite imagery, and this is on April 1st. And this is not because it is Fool's Day. It is because this is considered the last day when we already had the largest snowstorms. So this will be 2012. This will be 2013, so this is, we went to this is the second year of the drought. This is the third year of the drought. This is the fourth year of the drought. So we have the Sierra Nevada only being Sierra, without any Nevada. That's basically what it looks like. So we had literally no water on that year on the Sierras. We didn't have any snow. Then this will be the last year of the drought. Then what you're gonna see, the following is the wettest year on record. Okay. So, sorry, that was the drought. Now it comes the wettest year on record. Yep, that is it. That's the wettest year on record that we ever had in the last 100 years. It actually doesn't look as wet or as with a lot of snow as 2011. Why is that? Basically, we're having more of the precipitation now, more of the rainfall in terms of precipitation, in terms of rain, not that much in snow, and the snow is melting earlier in the year. So that's what is going on here. We have the next year, it will be below a little bit a drought year. Then we're going to have 2019, that it was a wet year, and this is today. This is as of we're speaking. This is to 2020. It is a drought year. So if we didn't have enough bad news this year, we have a drought. So, I'm sorry. There we go. Now, in terms of physiography, so the last point that I want to mention here, let me see, now it's working. So when the easiest way for me to explain you how rain and runoff are related, think of California as a bathtub. And basically the rim of the bathtub is, in this case, it will be the Trinity Alps, the coastal range, the Sierra Nevada, the Tehachapi's, and again, the coastal range. So that will be the rim of the bath. And think that the bath is filled with sediment. So this sediment, that is the Central Valley, okay? In the walls of the bathtub, we have, or here in the Sierra Nevadas, we have a process that is called rainfall runoff. So all the water that it rains in terms of precipitation of rain or snow, it will end up either in the soil moisture part and then as water in the rivers, or it will be taken from the soil. It will be taken by the plants from the soil and setting into the atmosphere. So underneath the soil in these areas, it is pretty much bedrock. It is a lot of rock where we do not have that much volume to store water there, okay? Now, it is different in the valleys. In the valleys, we have, it can rain, it can be runoff, but water can permeate into that sediment that is at the bottom here. And as it is at the bottom, it will infiltrate that water in the sediment and it will recharge aquifers underneath the feet. Why is this is super important? Well, basically it is important because what you can think of is when you are on a hilly part of the state, and that can be on wine grapes, some tree crops, they are planted on the hills. Basically, the process that you're going to have there is a rainfall runoff. So the water will end up either in the river or it will be taken by the plants. If you're in some parts of the valley, the Central Valley, Salinas, all the different, Anderson Valley, Ukiah Valley, Santa Maria, Santa Margarita, Oxnard, Imperial, they are valleys, and they basically, there are aquifers underneath them. So what it rains, some of that will be taken by the plants, some of that will end up in the river, some of that will end up in the aquifers. So in the case of the Central Valley, the outlet is here in the middle of the bathtub. Most of the valleys, actually, they have, at the end of the bathtub, they have the outlet, which it will be how the rivers are draining into the ocean. This will be this exactly same concept. Now imagine that we're cutting, slicing that bathtub. Okay, so let me talk about the system. So what you're seeing here, and if you were taking this class in person, this is a model, a physical model. It is like a fish tank. Think of a fish tank or an ant farm. And basically, what you're seeing here is that it's filled with some sand, coarser sand, finer sand. This part here, it is very fine clay that it has been compacted, okay? This pipe that you're seeing here, it has holes underneath. So when I'm putting water or we're pumping water through this, water will come through those holes. and that will be kind of a representation of what I was talking, an atmospheric river. This portion in here, think of it as a river that we're cutting. That will be a river. Now here it will come to two very important concepts. One is groundwater and the other one is an aquifer. So when you have water, when you have a soil ground that is surrounded by water, that is groundwater. If you have a particle of soil or many particles of soil that are completely surrounded by water, that is called groundwater. Okay, the water is stored in the ground, any soil. Okay, now aquifers is the storage, is the bucket that is storing that groundwater. So aquifer is the container, and the water stored in that container is called groundwater. So those are two very important points. In this case, this upper aquifer will be unconfined, and it is unconfined because it has access to the atmosphere, or the rain can directly recharge it, and it can move right and left. This confined aquifer is confined by a confining layer, so it is encapsulated. This will be completely confined if in this area, this column of water has a screen, so water can come from this column of water into here. But if this was closed, it will be a completely confined, a completely encapsulated aquifer. And because it is not, because it has that screen, is semi-confined, so it is partly confined. These are wells, and literally this is how you can, this is just a pipe, and at the end, if you have seen any of the cases, it is, imagine like a pipe, a steel pipe that has a lot of holes, a lot of slots. That will be how it looks a case. And you can have it in the upper or in the lower aquifer. And piezometers is like thermometers, but for groundwater. So basically they measure how high or how low is the water table in the ground. And these are alluvial fans. So we have is the confined aquifer also called a bolson? No, bolson is a different one. But basically bolson, it means that it is a big reservoir, a big aquifer underneath. And I think that is a very old Spanish way of talking about aquifers, deep aquifers. Okay, so I'm gonna tell you how water happens or occurs in California using this, which is basically a couple of videos. In the winter, basically what it will happen, let me see. Okay, so we're gonna have some rain and you're gonna see water coming. So I'm putting here the water table underneath the aquifer, and then imagine that it rains and water is pouring down the river. So I'm pouring water into the rivers. As water is passing through all the different rivers, notice how the groundwater level on the right column and the left column is increasing. What that means is that rivers are not completely impermeable. They will actually recharge and infiltrate water to the aquifers that are underneath. Ultimately, if I give enough time, the water table in the river and in the aquifers will be the same, will be at the same level. The other important part of here is that we have, this is a losing river, a river that is recharging or is losing water to the aquifer. The next one will be, so now we are into winter. And think of winter now that is not the first rain. Now we have all this water, December, January, February. We have all the water pouring from this atmospheric river. And here we're seeing two different things. So one, I want you to notice where is the water level of these two columns on the right and left, okay? So what is going on is that water is putting in through this, through the atmospheric river, and it's now filling the sediment. As it is filling the sediment, it's also recharging the aquifer here. Also in this area, you're gonna see that because the soil cannot drink water as fast as possible or that fast, we're actually having runoff. And that will be runoff that is going into the rivers. So basically that's what is going on here. And look how all the not only the aquifer, but also the rivers are getting full. That's super important. That's why it's important to let rainfall infiltrate into the soil, because it's recharging the aquifers and it will also help the rivers. Okay, now here I think we are gonna have, so that was winter. Okay, so I think now we need to launch the pool number 2, and I think Maria in that one will help me a little bit with this. Yeah.
Sam, while people are responding to the poll, there's a question in the chat, and I was hoping you could respond.
That one of the bolson, that's what you were saying?
Yes.
Yeah, it is. Bolson is a very old Spanish word to refer to aquifers. So aquifers, they are also called bolsones. It's very old. This is kind of a Spanish 1800s.
Okay, thank you.
Some of them, one of the most famous is the one that is underneath the city of El Paso, Bolsón del Hueco. That's one of the aquifer names there. So I think, Ricky, oh, I see. So in the spring, groundwater recharge is mostly likely to occur. Rainfall and snowmelt. Yeah, both of them are correct, but it's mostly snowmelt. So basically, think about this. This is a spring, you have a lot of water that it is now melting. So most of the water in the rivers will come through that melting of snow. And as they are passing the valleys, it will be recharged through snowmelt. So let me go to the next one. So now we're in spring. Something that, as I was explaining this. Okay, so let me actually, well, the video is going on there. Okay, so right underneath here, we have a picture. And this picture is depicting how on this right side, the Sierra Nevada, and then in the middle, the valley. As you're seeing here, as rivers are leaving the Sierra Nevada into the foothills, the slope is actually pretty steep, or is steeper. What that means is that the river, it has a lot of energy going down. And when it has a lot of energy, the river starts carrying things to release that energy. What is it carrying? It's mostly sediment. It can be boulders, that will be in very large events, but pretty much gravels, pebbles, sand. When it enters the valley, all of a sudden it doesn't have that much of a slope and the channels open. So all that energy gets dissipated, and as it gets dissipated, it can no longer keep carrying those materials, those sediments. So it deposited in there in a form that is called a fan. And the type of material, this kind of gravels, pebbles, cobble, sand, is called alluvium. So those are called alluvial fans. It is just that's the term in these kind of areas where the river leaves the sierras, the foothills, into the valley, that area there. Why these alluvial fans are so important? Because as water is passing, think that water is passing through that specific material, that it has a lot of holes. It is very porous. So it will recharge a lot of that, the aquifer. In these areas, there are key places to recharge aquifers. In this case, in the model, we are using these two water columns as those alluvial fans, as depicting those alluvial fans. And basically, what you're gonna see here is that as I am, okay, so, let me see if I can stop it. No, it went down, sorry. I want you to notice these two columns. So the column of water is coming in here, and then I'm gonna pour more water. And now notice how water will start moving slowly but surely into the river. And basically, these alluvial fans, it gets into the ground, and it will start increasing not only the aquifer storage, but it will also discharge that water into the rivers. The most important, well, so that will be here. The most important part about this is that, or something that you need to understand, is that rivers recharge aquifers. Aquifers recharge rivers. Having a healthy river means that we're gonna have a healthy aquifer. Having a healthy aquifer, it means that we're gonna have a healthy river. Everything is connected. It's just a matter of time.
I'm going to go ahead and read the poll for the people who can't see it on their screen. So Sam wants to know, in the summer, groundwater recharge is most likely to occur through what? Irrigation, snow melt, or rainfall?
And this is during summer. So I have another question here from Carrie. I had a hydrologist friend from El Paso who told me about that bolson. They had set up a lot of denim laundries and live straws and co, and she said that the bolson was not recharged. That is correct. That the bolson del Hueco is it doesn't recharge that much. Pretty much it rains in that area between 10 inches to 15 inches. So yeah, they are just drying up that aquifer. That's super sad. Mm-hmm. Yes, you're right. 57% responded that most of the groundwater recharge come from irrigation. That is true. So it doesn't rain in summer. That was part of the Mediterranean climate. And all the irrigation or some of the extra irrigation that you're putting into the crops, it will end up as either runoff in the ditches or recharge in the aquifer. Yeah. So the last part of this is summer, and basically here in summer, okay, let me see. So I need to stop it. Okay, so what I did is I emptied the river, and then all the water that was stored in the aquifer, it will continue to let me stop it there. So here, so basically the river and the ground and the aquifer were at the same level. I took the water out of the river, and as you can see, slowly but surely, water from the aquifer is start refilling the river. If it hasn't rained in 6 or 4 or 5 months, so I'm emptying it there. So look, I put that hose, that water, I put it down. So I just empty that one. And water from the aquifer will start permeating into the river. That will be a gaining river. Now I'm gonna extract water out of this well using this syringe. And as I am doing it, and of course you're thinking that you're extracting groundwater, the reality is that it is also, you're gonna see that how the water level on the river goes down. Everything is connected. You may think that is groundwater, it's just water that is connected with the river, and as you are depleting the aquifer, you are also emptying the river. So I think that will be it for me, Lisa.
Okay, so I'm gonna talk about, now that we have this good basis for like how water moves through moves through the soil and moves through the system, and when we get water and when we need to rely on irrigation, we're going to talk about just the general ways that pesticides can get into water. So based on your soil properties, your pesticide properties, and your applicator practices, pesticides can get into the water. And so you need to know a lot about these 3 components of your management system so that you can control to the best of your ability how pesticides get into water through leaching, running, and direct channels. So I'm not ignoring all the other ways that pesticides can get into water, like, you know, just dumping it directly into the water, pesticide applications to water, drift adds pesticides to water as well. But we're going to focus on leaching, running, runoff, and direct channels. And we're also going to focus on how to identify the soil properties, pesticide properties, and the correct applicator practices to prevent these mechanisms. So when we talk about soil properties, what we're really going to focus in on is the soil texture. So whether you have silt, clay, or sand, that really impacts how water and therefore pesticides move through that soil. The depth to the groundwater is really important because you know, how deep the pesticides have to travel in order to get to the groundwater will determine whether or not you have pesticides in your groundwater and or surface water. We're going to talk about groundwater protection areas, which are real sensitive areas. Pesticide properties that are the most important and that we'll focus in on are persistence, solubility, and absorption, and I'll define all of these in just a second. And then the applicator practices, which is what you have control over, right? Monitoring the weather, thoughtful irrigation practices, reading and following all label instructions, and Maria can tell you more about that next week on our label reading webinar, and good application practices. So basically, this is just a quick infographic. I'm just going to say it's an infographic. It's really just a graphic with information on it. So infographic of how pesticides dissolve, the fate of the pesticides in the environment. So we can have, actually what we're going to focus the most on is percolating or leaching through the soil to end up in groundwater, and also overland flow or surface water runoff. Okay, there are lots of other ways that pesticides degrade in the environment, and it's expected. So photo degradation, volatilization, some measure of that is expected, but there's lots that we can, a lot of practices that we can implement to prevent some of that. So I have a poll for you. So Sarah's gonna launch the poll. And so the poll is, under which soil conditions are pesticides more likely to leach through the soil? Is it clay soil and deeper groundwater? Is it clay soil and shallow groundwater? Or is it sandy soil and shallow groundwater? So like, I would never put this question on a test because you can't have a double answer, because it's just kind of mean, but it's the poll. We don't, it's anonymous responses. We just want to get you to thinking. So sandy soil and shallow to groundwater. So each of those individually certainly contributes to leaching, but both of them put together is significantly contributes to leaching.
Okay, so we're gonna, this is of all the things that we're talking here, these are eight clear steps that you can follow to prevent pesticides getting into water, and the same as fertilizers. So the first thing is that you need to identify the soil texture of the field that you are working, and of the space that you're working. This is the triangle of the different soil textures. It can be clay, sandy loam, sand, silt. This information is available for the entire state of California in here. So you go to this link, and you can actually get what is the composition of the percent of sand, soil, and so on, and you can use those percentages in this triangle to estimate if you have a clay loam, a clay, a silt, a sandy loam. So that is step one. Get your soil texture. The second step is, in this website, you can actually get the deepness to the groundwater. So you can see how deep is the groundwater on the location that you are. Then you can go, so that is step number 2. Step number 3 is figure out if wherever you are in California, there is a groundwater protection area, a GWPA. These are the counties that have GWPAs, and associated with this, it comes a map like this, where you can identify if there are certain regions that in this case are a protected area because of runoff. What does that mean? That if you apply a pesticide and there is any runoff out of that specific field, it will end up in the rivers and contaminating the water. Or in some of these cases where if there is any leaching of the pesticides, it will end up in the ground because this can be aquifer recharge areas. So that's what you're going to be seeing. So number 1, soil texture. Number 2, it will be the depthness, the deep to the groundwater. Number 3, these GPAs. Lisa?
Okay, so going back, okay, I'll stay here for a second, then I'll go back to the map. Should have repeated it. So a groundwater protection area is a 1 square mile section of land that is for some reason vulnerable to pesticide movement to groundwater. And it's because of the soil texture, the depth to groundwater, or some combination thereof. So if you look at this, the groundwater protection area maps, that this is all managed by the Department of Pesticide Regulation. And in 2020, some of the counties that already had groundwater protection areas had more added to them because they're doing a much better job of sampling these days. And so they're learning more. And so things change as we learn more. But when that changed, their maps changed a little bit. So it's not as easy to see the legend. So the legend says leaching or runoff. So certain sections of land are more likely to lead to leaching or runoff. And what these groundwater protection areas mean is that there are certain pesticides that are restricted in those areas. So if you find yourself in one of these squares in the map, like obviously landforms don't exist in nature in like an exact square. This is a gross map. You would have to go to your county ag commissioner's office to get a more detailed map to figure out exactly where you are on the map and to see if the groundwater protection area is exactly where you are, right? So there are 2 lists of pesticides that have this potential to, that in California have been identified as having the potential to pollute groundwater. So there's the 6800A list. So this is 3CCR 6800. This is a list of 7 herbicides. They're all herbicide active ingredients that have previously been found in groundwater because there's something about this pesticide that makes it more likely to end up in groundwater. Okay, and they're all regulated in a groundwater protection area. There's also another list. It's a much longer list. It's got some insecticides and fungicides on it as well. It's called the B list. And so these pesticides are not found, but they're determined from some risk assessment to have the potential to contaminate groundwater. And basically the department chooses like a certain set of these B list pesticides in a year to do hardcore monitoring on, just to see what's going on with them. So they're like giving themselves permission to monitor for any of these 98 pesticides, even though they don't do it very regularly. So these are the pesticides. On the left, it's the active ingredient, and the right is like an example trade name. I'm not endorsing any of them. I'm not saying anything yes or no. These are just pesticides that are very likely to be found in groundwater, and so they're restricted in these areas that have sandier soils and have a shallow depth to groundwater. So pesticide characteristics that lead to water contamination, as I mentioned, it's persistence, solubility, and absorption. Those are the 3 most important things, and I'm going to define each one of them. So persistence is the time that it takes a chemical to break down in the environment. So, you know, when we have an herbicide and we apply it directly to the soil, and it's soil active, so it's killing the seeds and the germinating seedlings in the soil, we love persistence, right? Because it stays there for long enough to keep killing the seedlings so that the more weeds don't emerge later in the season. But the thing about a long persistence or a long half-life is that it increases the likelihood of environmental contamination. Whether you're talking about leaching, runoff, drift, any pesticide or any chemical that stays in the environment for a longer period of time is more likely to contaminate. So this is something to always keep in mind. Certain amount of persistence is good, so we don't have to keep reapplying. But after a certain point, it's like very persistent in the environment, and it is more likely to contaminate. So persistence is measured in half-life, and it's the time it takes half of the parent molecule to break down in the environment. So there's a range of half-life. So if you know the half-life of your chemical, you know if it has low, moderate, or high persistence based on this chart, rubric, whatever have you. So water solubility is the amount of pesticide that can dissolve in a solvent, and usually it's water. So we'll just assume it's water because we're talking about groundwater. So not all pesticides are soluble. They don't just like dissolve and mix in the water completely, okay? So if you've got something that is more soluble, And especially if it's soil applied, it's just more likely to move downward in the soil. So there's like a different range. So low water solubility is something like this. See all these pesticide, oh my goodness. All of these pesticide particles that are just, they're not dissolved in the water, whereas this is, right? So moderate solubility, there's different ways to measure solubility, or different scales to measure solubility. So there's more pesticides like actually actively dissolved in the water. And then it can get all the way to high water solubility. And you can tell we got these GIFs or GIFs, whatever they're called, from the herbicide properties tool. They're found on the National Pesticide Information Center website. And so they've got an herbicides property tool. So they go through so many common herbicide active ingredients and tell you the persistence, the solubility, and the absorption, okay? And so that is a very helpful information. So adsorption is the tendency of a pesticide to cling to the soil, right? So a pesticide that has a high adsorption coefficient, higher binding capacity, is less likely to dissolve in the water, okay? So it's more likely to stick to the soil property particles, and then if there's excess water, it'll move overland. And now I know where I should have put that infographic. I'm gonna have to go back to it. So both the soil and the pesticide factors influence adsorption. So it's measured in a KOC, which is the adsorption coefficient. You don't have to measure it, you just have to know what it is. You can find that in the herbicide properties tool. And also soils like heavy clay soils have more binding sites. So pesticides that have the tendency to bind are more likely to bind to a clay. So I'm going to go up a few slides, please pardon me. And I'm going to go to this one. I should have put it way further down. So our pesticides that are fairly persistent, so they stay in the environment wherever they are, if they're soil applied and they have a high adsorption coefficient, so they're more likely to stick to the soil, and they're in a clay soil, and then you have excess water, they're going to be stuck to those soil particles. And so when you have soil erosion, you also have water contamination of the surface water, okay? And then if you have a pesticide who's kind of the opposite, right? So it's in the environment for a long time, it's very soluble, and then you have excess water, it's going to dissolve and move down to the groundwater. But remember what Sam taught us. That is the most important thing I think that Sam has taught me in all the years that I've known him, is that groundwater and surface water mix. The rivers recharge the aquifer, and the aquifer recharges the river. So don't think, oh, well, we use groundwater here, I don't care about the surface water, or vice versa. It's all important because it's all connected. It's just a big cycle. So we need to protect all of our resources, is what I'm telling you. So we've got solubility, adsorption, and this is, if you look at the sort of like this combination of a half-life and the KOC, like a persistent soil that really is absorbing, it's going to have this high groundwater ubiquity score, meaning it's just going to stay there for a longer period of time. So let's do poll number 5. So the poll number 5 is, as a pesticide applicator, which of the following things can you influence in order to prevent contaminating water with pesticides? Is it the chemical characteristic of the recommended pesticide? Is it irrigation scheduling, or is it depth to groundwater? So maybe if you're in the situation where your PCA has recommended a pesticide and your job is to make that application. So maybe you have control over what pesticide is being applied, or maybe you don't. I think it depends on what our job description is. Okay, so it looks like a fair amount of people have responded, and a lot of people said the chemical characteristic, and almost as many people said irrigation scheduling. So the one thing that, you know, if you're sort of like the land manager, yeah, you can say, hey, we just applied a pesticide to the soil, it's really soluble, we're going to wait on the irrigation, right? You have a lot more control over that. So you can't really control the chemical characteristics of the pesticide you're applying. You can control what pesticide you choose, But that sort of depends on, what your relationship with your PCA, or maybe you make those decisions. So it is a little bit of both. You certainly cannot choose, you don't have any control over your depth to groundwater. So the things that you can do as an applicator are monitoring the weather, right? Because any amount of water directly following a soil applied pesticide, or like any kind of pesticide application, could lead to leaching or runoff. Okay. And so if you're in a situation where rain is forecasted, you might need to make some decisions about when and if to make your pesticide application. So irrigation practices, keep an eye on your soil moisture, because if your soil is saturated, it's more likely to have a runoff effect. But also if you can schedule your irrigation to coincide with your pesticide applications in the correct way. Reading and following all label instructions, because there's some information on the label that is really going to help you do the right thing. And then just having good application practices. So I'm going to turn this over to Sam so he can talk to us a little bit more about runoff and how the model shows up runoff.
And here is just emphasizing what Lisa mentioned. So if it is raining so you applied pesticides, and then it is raining heavy, or you applied a lot of irrigation, which is a man-made rain event. So we apply it, and then if it is saturated the soil, the water will start moving also the sediment. And as it is moving the sediment, then with the sediment will come the pesticide. Or if it is over-applied, it may also leach into the aquifer. This you have already seen it. So here you're seeing surface runoff from the field into the river that will move some sediment in here. Also, if there is, again, a heavy rain or an over-irrigation event, it will recharge the aquifer and pesticides will end up in the soil. Here by the end of here, you're gonna see that there is some sediment in here, and if the pesticide was bind pretty well to the soil, it will end up in the river. So these are the 6 steps that we were discussing. So first thing, you go and this is for an example that we did in downtown Sacramento. So the soil texture there in the map, we find that it was silt. The depth to the groundwater, 70 feet under the ground. That specific location was not under a groundwater protected area. Then the second thing that we did, we went to this specific database, and then this is what it comes. Really, this is how it looks: water solubility, vapor pressure. So the persistence is 293 days. It's going to stay more than half of the year. Half of it will be more than half of the year in it. So you apply it, you likely come the next year, and it will still be there. And solubility is not very soluble, but it has a lot of absorption. What that means is that binds pretty well to the soil. So these will be the other 3 steps that you have to do, going through this database. Once you have done that, then you need to make a diagnostic. So it is very persistent and it binds very well to the soil. What that means is if you have a heavy wind or an over-irrigation event or a lot of rain, and the rain carries the soil, it will move where the soil moves. And it can be through irrigation, rainfall, or air drift. Basically, that's what it will happen. Yeah, the soil will move into the surface water. So what are some of the BMP's practices that you can do? Can you change the pesticide for a one that is that doesn't stay that much on the environment, but it doesn't bind very well? Do you have any control about the applications? Monitoring the weather. Be conscious about the irrigation practices that you're putting in there, and as always, reading and following the label. The next example is the same, so I will skip it for the sake of time. And now we're going to be talking about leaching.
So you guys have seen this video. Maybe I'll skip this video. It's just a reiteration of the video. So assuming that we have, okay. So atrazine is one of those 6800A chemicals. It is commonly found in groundwater, like everywhere you go. Okay. It is moderately soluble. It's also, so we've got a soil texture, which is silt. It's kind of a moderate soil texture, a shallow depth to groundwater. We're not currently on a groundwater protection area, but it's a fairly persistent pesticide, okay? And I get all of this from the herbicide properties tool. You just type in atrazine and this whole thing comes up, okay? And then it is moderately soluble. So, and it does not bind to soil. So the fact that it's a little bit soluble and pretty persistent and it doesn't bind to the soil at all, that means when you have excessive irrigation or excessive rain directly following this application, it is going to move through the groundwater this way. It's going to go all the way down. It is just not going to stick in that soil profile. So this is what it's going to look like. Beep. So I'm going to skip this poll. I'm going to tell you the answer. Herbicides are more likely to be found in groundwater and surface water, in part because herbicides are much more likely to be applied directly to the soil, and they can, and for that reason, and also because we want them to be persistent. So it's more likely to be herbicides.
And just something super important there. If it ends in the river or if it ends in the aquifer, that's where actually most of the intakes for the water that you receive at home, that's where they come from. So we really don't want to have water in the ground or in the rivers because that's the water that you're opening on your tap. Sorry, just wanted to reiterate that.
So I heard a presentation one time from somebody in the environmental monitoring department who's a high-level supervisor at the Department of Pesticide Regulation, and he said, I'm quoting, "If you follow the label, you're cool." Meaning, if you follow all these label requirements and all the California regulations, you are doing your part to protect groundwater. So there's label instructions in addition to doing the irrigation thing, right? There are label instructions that tell you different ways that you can prevent groundwater contamination. So for example, if you look at trifluralin, which is one of the examples that Sam gave before, there are very specifically different rates for your different soil textures. This is a soil applied pesticide. So if you have a sandy soil, you're going to have a different pesticide application rate than for a clay soil. And it's because it is persistent and it can run off. Also, if you have a restricted pesticide due to toxicity to aquatic invertebrates, that you need to keep those things out. You need to be extra careful, and there's probably extra restrictions written into the label because those cannot end up in the water. And this is why we're protecting water, right? Because there's aquatic invertebrates, we use it for recreation, we use it for drinking, okay? And all the other things that we use water for. So you can learn a lot more about proper pesticide mixing, loading, and storage in our book, The Safe and Effective Use of Pesticides. We're also going to do some more webinars specifically on that topic. So let me just launch this poll really fast. So we're going to launch poll number 7 on wellhead protection. So pesticide mixing and loading should occur at least how far from a wellhead? Is it 50 feet? 100 feet or 200 feet. So it looks like most of you know this. It's 100 feet, and it's because it's written into the regulation. There are some exceptions, but really good applicator practices are to keep because accidents happen, right? And we can spill pesticides, and you would not want to spill a concentrated amount of pesticide right next to the wellhead. This video actually goes really fast. So you miss a little bit of the first part of this video where Sam has accidentally spilled a red pesticide into the system. Okay, so it was going fast earlier, but so see how the red moves throughout the system? It looks to me like the video is not advancing. Is that right? Or is it advancing?
It is not advancing.
Okay.
But definitely
this video is a big problem. So let me see if I can get it to the end. So the pesticide was spilled here. And remember, this is our well. And so see how the pink, it's pink, but look, it's here, it's here, it's here, it's here, okay? It permeates throughout the system. So you've got like a really concentrated amount of pesticide. That's why we don't mix and load right next to a wellhead, okay? Okay, so in summary, it's amazing that we end these things on time. In summary, Choose pesticides that are not likely to leach or run off. If you have that autonomy in your job to make those decisions, then look into the herbicide properties tool. And if you're applying like an insecticide, for example, some of those are soil applied as well. Any soil applied pesticide is you need to be very cautious about and follow all those label instructions. You're gonna have to look a little bit deeper for a non-herbicide to get information about the GUS and the KOC and the absorption and all of that stuff. The herbicide properties tool makes it really easy. You can find some of that information in various databases, and I can provide you with that in a summary email that I send. I forgot to add that here. And you can get some of that information from an SDS as well. But in my experience, the information on the SDS, like for environmental contamination, is not consistent from one pesticide to another. So it'd be hard to compare. So you need to monitor weather conditions and schedule and monitor irrigation appropriately, because the last thing you want is to have a heavy irrigation, you know, like an irrigation after a pesticide application, okay? Unless your label instruction asks you to add like 1 inch of water to help incorporate.
Don't
So
do it.
Follow those label instructions and also mix, load, and apply pesticides properly. So I haven't been monitoring the chat, so if I need to respond to something, somebody should tell me that right now.
Yeah,
So there are some resources here for you. We'll send them, again, we send an email with the verification of attendance with a compilation of all these resources. So the herbicide properties tool, just Google it. And then groundwater protection areas, those are California specific. Check your weather service. I know a lot of people have different methods that they use for checking the weather, but keep on that. You know, people in the agricultural community are more in tune with the weather than anybody else I've ever met, except for los campesinos in Panama. Ellos hablan mucho they talk a lot about the weather. Your local ag commissioner's office will be extremely helpful for you. There's a link here for Hydrology 101, which is like more in-depth information presented by Sam. And then our UCIPM pest management guidelines, they have a lot of information to help you choose different pesticides, okay? And then we're going to have more webinars on storage, transportation, mixing, loading, pesticide label reading. So go to our website, figure out the webinars, and then also this book is super great. So if you have any questions, we're here, okay? I just wanted to make sure everybody had a chance to see this picture because it's, okay.
I think in that one, there was one question, Lisa, related with plastics, microplastics. So if a pesticide attached to a microplastic and then where does it ended up, the microplastic, is something that they should care about or that we should?
I don't know. What is a microplastic? Are you talking about, maybe if I have more information about a microplastic, that would be very helpful.
So basically, let me see if I can find it here. Oh, it says under SB 1422, do pesticides attached to plastics, microplastics, and allow them to hitchhike into water bodies? It is kind of the same as a soil. Right. So the pesticide attached to the soil and then the water hitchhike with the soil.
You know, with those microplastics, I don't know if pesticides can actually bind to them. I don't know if they have good binding sites. I don't know enough about the chemistry of plastics, but I would just say if it does bind there or stick, and then that microplastic ends up in the water, then absolutely the pesticide is there. And if it's persistent.
So Kim, can we revisit water solubility? That section went at least fast to me.
Okay, Kim wanted to revisit water solubility. Are you still there, Kim? I hope so. Okay. So basically, so solubility is measured in milligrams of pesticide per liter of water. So like the more, the heavier weight of a pesticide that can dissolve in water, the more soluble it is. So there's certain pesticides, so there's like different formulations, right? Like soluble liquids, they're much more likely to dissolve in water. They're water soluble. But as you know, like many of our pesticides have like oil in the mixture, particularly an emulsifiable concentrate. They're not particularly water soluble. They may emulsify in the water with the tank, but they don't necessarily dissolve. So it's hard to really know if your pesticide is dissolving unless you know the solubility. So water solubility of the pesticide is important. It's the amount of that pesticide that can dissolve in a liter of water. So, you know, going back to chemistry 101 in college, it's like dissolves like, right? If you've got a water soluble material and it's in, you know, like a hydrophobic versus hydrophilic. I'm not a chemistry teacher, I'm sorry. Some things are just do not dissolve in water because they're not close enough to water in order to dissolve.
And the other important part about this is that it's not that you have to figure this out for yourself. You can go to the website that we send you, the National Pesticide
Information
Center. And basically it will tell you if it is low water soluble, medium, or high. So it actually tells you what is the solubility. What we're trying to encourage is that you go actually to that database and you look at what is the solubility, and base it on that. The main characteristic of soluble pesticides is that it will end where the water ends. So if you over apply it, over irrigate, it will go down into the groundwater. If you apply it, if you didn't apply it that much, but you have a rain event, it will, again, it will leach, it will get into the groundwater, or it will go into the rivers. And I think that's the main, that's the key message here.
And also, I mean, I think Carrie is the one who mentioned it in the chat. It's not just pesticides, it's any contaminant. So fertilizers, right? This is why nitrogen ends up in the groundwater, because nitrogen is soluble, just like, I wish I knew the mgs per liter. Maybe it's just like atrazine. So it's a chemical, you know, a pesticide is a chemical, a fertilizer is a chemical. These are chemical properties. This is not anything unique to pesticides. It just happens to be what we're talking about pesticides, so that's what we talk about.
No, is the opposite. Low is more hazardous to groundwater contamination.
Something that is highly soluble means there's more pesticides in the water. More pesticides in that soil water. And the soil water is what goes downwards. So the more of these particles, see, some of these particles are just sitting at the bottom with low water solubility. It means it's not in the water. It's not going to move with the water. So there's fewer particles that are just sitting there doing nothing. And here, when it's highly water soluble, it means there's a larger quantity of pesticide in that same container of water. And so whenever that water moves, more pesticide goes with it. Cool.
Yeah, thanks, Kim. Thanks for asking that one, Kim. Okay, are high volume or high concentration of herbicides application more likely to lead to groundwater contamination? No, okay, so James, so high volume, it doesn't mean that it's high concentration. So you can apply, I think more than the high volume or the high concentration, I think is well, it will have to go with the solubility. So how soluble is the pesticide? So that's number one. And yeah, after that, it will be the high volume. So if it is soluble and you're applying a lot of water.
Yeah, and I think, so herbicides are more likely to be found in the groundwater because they're the pesticide type that's more likely to be directly applied to the soil, and sometimes even to bare ground. So there's no plant roots to like grab it in the soil, and it's done on purpose. But also somebody at DPR did tell me that it's also in part because the amount that you apply is greater because it is the soil. I don't really know that to be true. I'd have to like compare a bunch of different pesticides, but somebody from the environmental monitoring department did tell me that herbicides are applied in higher, like just more pounds per acre, I guess you could say, or more ounces per acre. But it honestly depends on the herbicide. But they are more likely to be a soil applied, and oftentimes to bare ground. And they're often persistent because we want them to stay in the ground, killing those seedlings as they start germinating.
But so first, take a look at the solubility and then the volume to not over irrigate.